Okay. So can you still hear me?
Yes,
Weird. Okay.
that's good. Thanks.
So yeah, so about the numerical calculation then. So what we did here is we imposed the unitary gauge and also spherical symmetry, so that the Higgs doublet is parameterized in terms of only one field, this scalar field, which is only a function of the radial coordinate, so a function of r. And for the gauge fields, we impose the spherical ansatz, and this is the standard thing to do when you are computing this kind of topological solutions. So this is a parameterization of the gauge fields in terms of three scalar functions of r, of the distance from the origin. So in total, our field configuration is given by four fields here. So by four, let's say, profile functions. And our method is first representing these four functions using a neural network. So yeah, and for the purposes of this talk, I think we can just say that a neural net is a function that takes m real inputs and gives you n real outputs. And what function you have depends on the internal parameters of the net, which are called weights and biases. And if the network is complicated enough, you can reproduce any function that you want as long as you adjust these parameters in the right way. So this is what neural nets are used for fitting very complicated problems. In our case, we took a very simple network because our problem is, in this sense, it can be simple. So one real input here, which would be the radius, and one hidden layer, and then as outputs, four real numbers, which correspond to the values of the four functions that characterize our field configuration. So if we give it a value of r, it outputs the value of these four functions at that r. And then we need to train the network so that it solves the problem that we want to solve. And this is usually done by means of a loss function. So you have some function L, which you compute.
Excuse me, I
from
have a
the
quick question.
Yeah.
Is there a typo there, the boldface B and unboldface B in this formula?
I think they are bold because just to denote that they are vectors of the outputs.
Just that there's a BI superscript 1 and a BI superscript 2, and I'm trying to distinguish between those. Are they distinguished or?
Yeah. So okay, so this is first an affine transformation, which is the V1 and W1, then a sigmoid, and then you get to the first layer, to this hidden layer, and then you apply another affine transformation over this. These are W2 and B2.
So what is the total dimension of degrees of freedom there?
It's okay. That depends on the size of the hidden layer, which is, in our case, it was 30 units, I think. So this should be the dimensionality of an affine transformation from one real variable to 30, and then the dimensionality of an affine transformation from 30 to 4.
So it's in the hundreds.
About, yeah.
So it's very high dimensional. Thank you.
Yeah. So minimizing these loss functions, which are functions of all these parameters, it can be pretty complicated, but there are frameworks already designed to solve the specific problem that you find when you have a neural net. So it really is just a minimization problem of overall these parameters. And you choose the loss function so that minimizing it gives you the solution to the problem that you're looking for. So there are already,
There is a question from Linden. Maybe we can answer on the go. No? How did you choose the number of nodes in your hidden layer?
Just by trial and error. So um, I tried a very simple network with 10 units, and it didn't seem to fit too well or quickly enough. So it's just trial and error. It's very hard to know this in advance, I think. So this is one free parameter that we have here this is something like a hyperparameter because you fix it before you start training. There's also the depth of the network. You could also have other layers here. But I also tried that, and it didn't increase it didn't improve the fitting procedure much. So it was trial and error. So where was I? So concerning there are some successful methods for solving differential equations with neural nets already out there, and we could have used just one of those. So just find the equations of motion of our fields from the Lagrangian, then plug these equations into one of these methods, and we would get our answer. However, in our case, there was a simpler approach, and to the best of my knowledge, this is the first time that neural nets have been used for this purpose. So we decided that since what we are trying to do is minimize the energy, we could use as the loss function directly the energy. And if we are able to get to a minimum of the energy, then the equations of motion will be automatically satisfied, but we don't even need to know what they are. We just need the energy functional. We minimize so we minimize it and we get our answer. So the loss function is here is the energy plus a couple of terms that we need because we need to fix some things. So we need to fix the boundary values of the fields. So we have this term that is boundary conditions squared, and minimizing this amounts to making the boundary conditions 0, so they're satisfied. And the same for this extra term here in the next line, which is fixing the value of the winding number. So we want to be able to fix it to whatever value that we like, and we do so by including this extra term in the loss function. And then if we make these two weights that we have here, these omegas, large enough, minimizing L will amount to minimizing E while making these two extra terms 0. This is exactly what we would like to have. So we have our loss function, we have our network, and we can just plug it into some automatic framework for training it. We used PyTorch, and we get our solution once the network is trained. So our solution, the network itself, consists of 4 functions of the radial coordinate. 3 of them correspond to the gauge fields. So these were already present in the frozen Higgs limit. So they were computed by Ambion and Rubakov, and we get very similar profiles for them in our case. But now we have one extra field, which is sigma. This is the Higgs. And as you can see, as you go to infinity, its value goes to a fixed constant, which is its BEV. But near the origin, this field can go to lower values, and in this way make the energy a bit lower. So the frozen Higgs case would be having the red line here, the sigma, being constant. And here it is, you see, it goes a bit down. So this should be an improvement in the energy, so a lower value of the energy. And I forgot to mention, so I have 2 free parameters here: the cutoff scale that goes in front of the square operator, and the winding number. So this is for cutoff scale 200 GeV, and the left plot is winding number 1/2, and the right plot is winding number 1. So we are able to vary these two parameters and see how the solution changes.
I have a question if I could.
Yeah.
So the relaxation of this constraint, so this asymptotic value for the Higgs field, you indicate that that would be just a constant all the way to the origin, so to speak, frozen.
Yeah.
Is the energy in that case infinite?
No, I think it's finite.
Yeah, so the reason for asking is that in sort of in other contexts, you have this notion of you enforce or impose a winding number, and you minimize a gradient penalization in the energy, and the topologically necessary singularity gives you an infinite energy, but then you can relax that by allowing the core to dip away from the hard constraint. And so I'm trying to make the parallel here. Is this like a soft core concept?
I didn't think about it this way, so I don't know if you can think about it, but I mean, we ensure that there are no singularities at the origin by the boundary conditions. So maybe that's something different. If the singularity, so if the infinite value of the energy comes from some singularity at the origin, we don't have that. And I'm not sure if this is answering your question.
Yeah, I'm just trying to connect it with the things that are somewhat more familiar to me. So again, if I give you a vector field in the plane, and you have the disk, and the boundary condition is the normal vector field pointing outwards, winding round once. If I'm trying to minimize the integral of the gradient of that vector field into the interior, but I have the constraint that the vector field in the interior lives on S1, then I've got this geometrically or topologically necessary singularity, which would lead to a vector field with a singularity at the origin and just a constant radial field. But the energy is infinite. But I can relax that energy by introducing a potential which allows the vector field to relax as it gets close to that core. So I was just trying to make the parallel here.
Okay, maybe that's not the best analogy, because there you have, so the dimensionality of the space over which your fields are and the target space is different. So you have S1 as the target space, and you have the disk. But here you have S1 and S1, or the dimensional analog. So you don't have any singularity in that sense.
Thank you. Okay.
Just a comment, a bit running out of time. Of course, you can have a bit of extra time because there are many questions, but if you could maybe speed up a bit.
Okay, yeah.
Let's go to the point, and thanks.
So, okay. So let's go to the next slide directly. So one thing that we could do is try to see how the energy, so try to see the energy as a function of the winding number. Since we can fix the winding number and compute the energy of our configurations, we can do this. And these are the curves that we got for different values of the cutoff scale. And as you can see, there's a minimum at winding number equals 1. So this means that the skyrmion is still there. So we have found that the skyrmion still exists when the Higgs is taken into account, and there's a finite energy barrier, as one would expect, because this is not protected by a topological charge anymore. You can also see that as lambda is made smaller, the height of the barrier and the height of the skyrmion become closer, and at some point below 100 GeV, the minimum completely disappears. So there's no skyrmion anymore. By the way, the energy here, so the height here of the potential at winding number equals 1 is the mass of the skyrmion. So we studied how the mass of the skyrmion depends on lambda. Basically, we found that it's inversely proportional to lambda squared. So you can have a mass in natural units defined by stripping out this factor, which is then 0.35, And if you look at it in physical units, you include this factor, and then it goes down quickly with as 1 over lambda squared. And because these are lower limit on lambda, this means that there's an upper limit on the mass. So skyrmions of masses higher than 10 TeV cannot form, because this would correspond to values of lambda, very small values of lambda, which don't allow for the existence of the skyrmion. And these plots are just the same as I was saying with formulas, but with plots. So basically, this is the natural value of the mass as a function of lambda, and you can see that it's more or less constant. And this is the mass in TeV units, and you can see that it goes down quickly with lambda. And the orange line here is taking a very large value of the Higgs mass. So this should be the frozen Higgs limit. And this was a cross-check for us. So we just saw that we could reproduce Ambient and Rubakov's result in this case. Yeah, I can skip this. This is just, so we could also compute the radius of the skyrmion. Since we have the full field configuration, we can compute anything over it. And I can go to the phenomenology. So first, concerning the production and decay of skyrmions, this is a very similar process to an instanton. So this is a process that changes winding number by 1 unit, and that means that B plus L is violated by 6 units in this process. And it is similar also, of course, in the sense that you are you're jumping from some minimum of the energy over a finite energy barrier of a few TeV down to another minimum of the energy. And since instantons are exponentially suppressed, we expect that the same happens to skyrmions. So unfortunately, it seems that you cannot observe them in the near future in colliders. However, since the existence of the skyrm term with some value of the cutoff scale ensures the existence of skyrmions, one can look for skyrmions indirectly by looking at the other effects of this operator. So this is an operator with a lot of Higgses and W's, and you have these W fusion processes in which you generate several Higgses. We chose to focus on this left process as an example, and we simulated it with a math graph and tried to see what values of lambda could be probed at different colliders. So for this, we imposed that 300 events with this final state would be produced. So one Higgs decaying into gamma gamma and the other thing into BB bar. This is inspired by the most clear channel in di-Higgs production. And these are the values of lambda that we got. So LHC and high Lumi LHC are the first 2 lines. And as you can see, they wouldn't prove very interesting values of lambda. These are too small for skyrmions to be there. However, FCC 100 TeV hadron collider would be able to go up to 700 GeV, and this already proves a lot of the interesting values of lambda for us. And similarly, a lepton collider would also give us the same range of values of lambda to probe. We impose here 10 events would be observed, since this would be much cleaner. And yeah, this is a lepton collider at only 14 TeV. So in that sense, it would be as good as the FCC. And just the final point, a small one, but I think it's also important. As I said, the decay of skyrmions is exponentially suppressed. So we expect that they are very long-lived. And this means that they could be viable dark matter candidates. So we did this exercise of computing the value of the cutoff scale that would reproduce the correct relic abundance of dark matter if all of the dark matter was made of skyrmions. We took the annihilation cross-section. We just, as an estimate, we took the area of the skyrmion, so pi times radius of the skyrmion squared. and we got a value of lambda of about 2 TeV. Fortunately, lambda doesn't depend too strongly on the annihilation cross-section. So even varying the annihilation cross-section by 1 order of magnitude only changes the value of lambda from 2 to 3. And this not only tells us the value of lambda that would be needed for all of the dark matter to be made out of skyrmions, but also a maximum value for lambda. Because if lambda was larger than this, then we would have too much skyrmion dark matter. So yeah, so in this sense, we have a cosmological upper bound on lambda. And to finish, to conclude, I want to summarize what I have said. So we have found a new application for neural networks, and this is to solve variational problems. We have used this to show that skyrmions are still present when you include a dynamical Higgs field. The mass of the skyrmions scales as 1 over lambda squared, and it has a maximum value of 10 TeV. I haven't had time to talk about this, but we also checked that the Skyrm operator is generated in many simple UV extensions of the standard model. So it's reasonable to think that it could be there. And concerning the phenomenology, the production is at colliders is unlikely, but we can prove them indirectly through other effects of the operator that generates them. And they may be a viable dark matter candidate made only out of standard model fields. And this is all.
Thank you very much, Juan, for the nice talk. And there's time for extra questions. Please.
Hi, so you've mentioned how you've used your own kind of method of actually minimizing effectively the energy function or with some kind of extra constraints. Do you kind of have any idea of how well that works? For example, if I gave it, Yang-Mills Higgs and I was looking for the precise Sommerfeld monopole, would this method find that well?
I would guess so. I will have to try. This is the first time that I have done this, but so the main problem here is finding the correct values for these weights, I would say, because if the energy, you don't know the final value that you want to get for the loss function. Usually when you have a minimization problem for neural nets, your loss function should go to 0. But in this case, it goes to whatever value the energy has. So you need to have high enough values of these things in order for the conditions to be satisfied. But in principle, I think this can be applied to any variational problem, as long as you're able to play a bit with the weights.
Cheers. So there is Sven that raised his hand.
Yeah. So yeah, my question is also about this. You're using neural networks to solve. Basically, they are ODEs. Am I right about that? You're solving ODEs. They're not PDs. I mean, they're functions of R, or they are functions of 3D space-time.
They are only functions of R. Yeah. So
okay. So you're using neural networks to solve ODEs. Is that right? So
not in this case.
Not in this case.
No, here I'm not. I don't even have the ODEs. I didn't even compute the equations.
No, I mean, okay, there would be ODEs.
Yeah.
So yeah. But I mean, they're not PDs. You're not just plotting like a cross section of a 3-dimensional solution. So you could easily write down the equations of motion, and after having a solution, you could evaluate this equation of motion and see how well you found that. I mean, your solution, how well does it actually satisfy? Yeah. I mean, that would be easier than trying to solve them, just to see how good is the solution I have here. So I had another question. So you say they're pretty long-lived, these Skyrmions, but for dark matter, I think it actually matters what is long-lived exactly. Do you have any
the problem
any
is
good estimates for what is your long-livedness? Because your S field can, if your S field fluctuates on a different scale than the lifetime of the universe, your Skyrmions can disappear well before they have an impact on making star creations in the cosmology and so on. So it could be really important, like even a factor of 1,000 could screw it up.
Yeah, I agree. And we really don't have a good estimate of this. This is a pretty complicated calculation. So you would need to really compute the process of tunneling through this barrier to
Yeah.
you know. I mean, I would expect that this is something like e to the minus 1 over coupling squared. But beyond that.
Yeah. Okay, so thanks a lot.
You have many questions, so let's proceed in order. Next is Mark, please.
Yeah, I have two very quick questions. One is, first of all, the winding number can be negative also, right? So you also have skyrmion, anti-skyrmion annihilation. So did you take that into account in computing your relic density or something like that?
No. Okay. In principle, here the skyrmion and the anti-skyrmion are almost the same thing. Because there's no CP violation here. So
right, exactly. Okay. Yeah.
The potential is the same in the other direction.
Sure, but then they can annihilate in some way. Well, okay. Yeah. So let me ask you just another very quick thing: do you know the size of the Wilson coefficient in the standard model effective theory of the skyrm term? Is it bigger than other terms with 4 derivatives? Because I think in the chiral Lagrangian it's kind of an accident, but the skyrm term is in fact the thing that dominates at 4 derivatives.
But I'm not sure what you mean. You mean a measured value for this coefficient, or
if you write down the effective the standard model effective theory for the Electroweak sector, you will get this kind of operators, right? You're not assuming. So, exactly. So do you know if you write it, you probably have to change basis or something like this to see the skyrm term. But do you know if numerically this term with the commutator is kind of dominant compared to the other terms you could write down? Or
I don't. So dominant in which sense?
I mean just the coefficient is bigger or something like this, or. I mean, do you see, if you look at this effective theory, does it look like the skyrm model or something like this, or you just dropping the other terms, right?
I see what. Yeah. No, they are comparable. I mean,
they're not. I think it's a valid thing to do, but I think in the pion Lagrangian, for some reason there is even this accident that makes this skyrm model a bit better than expected.
I think there's at least another operator with 4 derivatives.
Oh,
so this would be the same order in the Lagrangian.
Okay, thank you.
So Apostolos, next question. You are muted.
I joined very late. I don't know whether this question I already mentioned before. I just want to know, just a matter of curiosity, if these skyrmions are topologically solutions of equation of motions, what kind of homotopy they have, because as far as I know, the standard model has no stable topological configurations.
They are not protected by any topology, really. They would be if there were no gauge fields and the Higgs was frozen to its PEF. So in this case,
but you cannot freeze fields. So there is a lot of literature actually in the archive, which half of them is wrong. And I don't like to criticize all this. This is because they say, I will freeze that, I will freeze this, and so you cannot freeze.
No.
There are monopoles. People, they think by changing the representation, they could do monopoles, other stuff, but they cannot do that. You cannot freeze by hand. So it should be dynamical.
Precisely what we do is we make it dynamical.
Yeah.
So it was known that from the old times that in the casing where it was frozen, it was protected and you had them there. And then we have checked that when you make the Higgs dynamical, it's also there. So it's only that,
So you are sure that you are doing dynamical and you are working the equation of motion, you get really that kind of solutions,
I'm not
right boundary conditions and all that stuff.
I'm not working with the equations of motion specifically, but it's a totally.
Yeah, if you don't work with the equation of motion, I don't see what is the upshot of this.
Sorry?
If you don't take the equation of motion seriously, I don't see the significance of these results.
No, it's of course I take it seriously. I mean, what I'm saying is that my procedure is the same as solving the equations of motion.
Maybe the comment of Sven is pertinent in this sense. You could cross-check a posteriori.
Yeah, this I totally, yeah. This I agree. And we didn't do this, but.
Okay, thank you.
Stefan, last question because we're really out of time.
Yeah, just quickly. I just want to get some clarity on the argument or the claim that your method is novel relative to variational problems.
Yeah.
So I mean, could you clarify what you mean by the novelty? Because the people I know in the mathematical community who work on variational problems, they would interpret many of these algorithms as variational. So in some sense, it's structure preservation. You have a variational model and you have a variational method, and you're integrating the two of those things.
Yeah.
So I guess is it true that no one's done this numerically?
So yeah, to the best of my knowledge, no one has done this. Of course, I guess many people have tried some family of functions parameterized by some parameters and use this to solve a variational problem. But specifically with neural nets, for which you have a lot of frameworks that can help you finding the solution. For this, I haven't.
Could you post this I'll chase it up, thanks. Could you post the relevant papers that you've worked on in this that I could look up and chase down some references? Maybe post that in the chat.
Sorry, can I?
Could you post some references in the chat so that I can chase this up?
I can give you references for solving differential equations, but I mean, I can't give you for the thing I think it's not there.
Okay.
I can give you for differential equations if that's.
Yeah, that would be great. Thanks.
Okay.
Okay, so we thank again Juan and